Let's look at the Chapter 12 review questions. Number 1, which of the following is not one of the conditions that must be satisfied in order to perform inference about the slope of a least squares regression line? So remember, your acronym for this is going to be LINER. And what that means is what we're looking for is that it is linear, independent, a normal distribution, there's equal variance, and that there's randomness going on. So let's take a look at it. For letter A, for each value x, the population of y values is normally distributed. That is going to take care of n, so that is adequate. For B, the standard deviation of our population of y values corresponding to a particular value of x is always the same regardless of a specific value. This is going to be talking about equal variance. I'm going to jump to E. The data come from a random sample or randomized experiment. That is our R. Letter D. There exists a straight line y equals alpha plus beta x such that for each value of x, the mean of y of the corresponding population of y values lies in a straight line. This one here is going to be the linear. Letter C, the sample size is the number of paired observation exceeds 30. There is nothing about sample size for this one, so clearly C is the wrong answer. Number 2, students in a statistics class drew circles of varying diameters and counted how many Cheerios could be placed on the circle. The scatter plot shows the results. The students want to determine an appropriate equation for the relationship between the diameter and the number of Cheerios. The students decide to transform the data to make it appear more linear before computing a least square regressions line. Which of the following single transformations would be reasonable for them to try? So if you look at this relationship now, it almost looks like it would be somewhat of a right side of a parabola possibly. So y equals x squared in this case, where we have the diameter is going to be our input on here, and this is going to be our Cheerios. So if I put it more into that relationship. One thing you can do to linearize it, this would be considered a power function because what we're seeing are powers in the equation. So in this power function, if you want to remove this power, one thing you could do is if you take the square root of the number of Cheerios, if you come in and hear what they're saying is you could come in and you could take the square root of the number of Cheerios, and that's basically just rewriting this equation. So it would look like D equals the square root of C, which really still gives us the same equation because we're just keeping it balanced on both sides. So technically, choice 1 is a valid option. Again, to reverse something in a powers, that is, if it's squared, you could take the square root. If it was cubed, you could take the cubed root. Because technically, you have the same equation, you're just rewriting it differently. Option 2 recommends cubing the number of Cheerios. Now, the reason option 2 is not good is it's talking about cubes. Right now, we're only dealing with more of a possible squared relationship. Or maybe it really was or could be a cubed relationship. Remember, a cubic actually looks something like this. But even if that was the case, let me show you. If this was cubic, it would have been this. Now, to linearize this equation, to come on in, they're recommending to cube the number of Cheerios. But if you came in and did that, and you actually cubed the number of Cheerios, you know, if you cube that to keep it balanced, you'd have to do that, which makes no sense because you're now getting an exponent to the 9th over here, so it's definitely not a valid thing. Now, what if they had said a different option, by the way, if this was our original function, if it was more of a cubic pattern, how could you linearize it? Well, you could take the cube root of both sides, so you could cube root the Cheerios, but not the cube. Okay, let's look at option 3. Option 3 is saying we should go ahead and take the log of the number of Cheerios. So you can do the log by reversing out exponential. So possibly what this is the Cheerios and then the diameter is an exponential. If it's an exponential function, it would make sense to take the log of the number of Cheerios because that's one of the formats we had talked about. If we have an exponential, you can take the log of the y value. So this is an option. Another way to look at option number 3 in a more general terms, we had said anytime we have an exponential function, the way to linearize an exponential is to take the log of the y. In this case, our y is actually the number of Cheerios, so that would be valid. Then part 4, take the log of the diameter. Now the problem here is that they want us to take the log of the diameter. Well, if it's truly an exponential function, if they want us to take the log of the diameter, this is our input, our x value, so that doesn't make sense. Exponential functions, we say take the log of our response variable, or the y, not the log of our input variable, or we also call our explanatory variable. So in this case, only options 1 and 3 are the valid, so letter B is the correct choice. Question 3, inference about the slope beta of a least squares regression line is based on which of the following distributions? So we learned in chapter 12, if we are going to do an analysis of a least squares regression line, we know it's going to be a t-distribution. So our choices here are either going to have to be A for the t, or it's going to have to be B. Chi-squared is for categorical data, so that doesn't happen. Standard normal distribution is when we have a normal distribution and we know the standard deviation of the population. And then the normal distribution with mean and standard deviation is also the same thing there. Just remember, this is regression. Regression analysis is an x and a y, or our explanatory and response variable. So to do that, we need the degrees of freedom of n minus 2. So the answer here is letter D. For the next 4 problems, let's use this scenario. An old saying in golf is, you drive for slow and you putt for dough. The point is that good putting is more important than long driving for shooting low scores and hence winning money. To see if this is the case, data from a random sample of 69 of the nearly 1,000 players in the PGA Tour's World Money List are examined. The average number of putts per hole and the players' total winnings for the previous season are recorded. The least squares regression line was fitted to the data. The following results were obtained from statistical software. The correlation between total winnings and average putts per hole for these players is what? Now remember, correlation is really what R is, so we need to find R. This output doesn't show me correlation, but it does show me R squared. Well, if R squared is 8.1% or 0.081 as a decimal, can we get R? Absolutely. Just come on in and take the square root of that. When you do that, you're going to get that the value is 0.285. Now the question is it letter E or is it letter A? Well, you have to look at the particular output. Remember from this, this is our slope, and the slope right here is a negative value. Because the slope is negative means if we were to graph the line, it's going to be going in a downward direction. Therefore, the correlation cannot be positive because correlation is direction with strength. So we need to show the direction by making it negative. The strength amount is the 0.285, so it's not the strongest line, but we do know that it's negative. Number 5, suppose that the researchers test the hypothesis, H sub O, that beta is equal to 0. H sub A, beta is less than 0, that is the slope. The value of the t-statistic for this test would be what? Well, if we take a look at that, we know for the t-statistic, the formula for that is it's going to be the value of the actual slope over the hypothesis of the slope over the standard error of the slope. So if we fill this in, from the computer output, the actual statistics slope was negative 4139198. The hypothesized, the beta of naught is 0. And then the standard error of the slope is the 169837. When you do this, you're going to get a t-statistic of negative 2.44. Question 6, the p-value for the test in the question is 0.0087. A correct interpretation of this result is what? Remember, a definition of p-value just means it's the probability of getting this particular statistic given the fact that H sub O is true. So if you just put that in definition, You could say something like, before even looking at the options, is the probability of getting this sample or anything more extreme is 0.87%, given the fact that the relationship between the slope is 0. So knowing that of these definitions, the one that is going to be the best answer is actually going to be D. And here's what that says. There is no relationship, because remember the slope is 0, between average number of putts per hole and total winnings for the winners of the PGA Tour World Money List. The probability of getting the random sample of 69 players that yields at least this square line with a slope of this or less is 0.0087. That's your best option. C looks like it might be a good option. So let's read it. Let me show you what's wrong with it. If there is no relationship between the average number of putts per hole and total number of winnings for the players, that's here, that H sub O is true in the sample. And this is the issue, as they said, within the sample. H sub O is true. Remember, H sub O, when we make that, we're saying about beta. This is about the population parameter. So we're not talking about the sample, we're talking about the population. So letter C is wrong because it says in the sample, whereas letter D says here in the PGA Tour, which is actually using the entire population. So be really careful. Those two are very close to each other. Now, another thing to point out, like with A and B, the problem with B says here, the probability that there's no relationship between the average number of putts per hole and the total winnings for these 69 players is 0.0087. It's this or more extreme is what they're missing. And again, they're talking about just a sample. Part B, the probability there's no relationship between an average number of putts per hole and total winnings for all players, so that's good, it's the population, is this. But it's this or value more extreme from what we're going to see. And then clearly part E, the probability of making a type 2 error. P-value is not type 2 error, so type 2 error is actually related to power. Number 7, a 95% confidence interval for the slope of the regression line is what? Well, if you look back at the output, you can actually write this. Remember, the formula is going to be this for the confidence interval. It says to do our B value, or our statistic, plus or minus the T critical value of the standard error of the slope. So when we take a look at the output, we know that the slope is negative 4139198. So from that, we can cross off A and B automatically. Now it's going to be plus or minus. We're going to have to find that critical value. The standard error of the slope, remember for that, is going to be, it looks like on the output, 1698371. So it comes down to finding the critical value. C is out because they didn't use the critical value. They ignored the T critical value. So to find the T critical value, remember it's going to be inverse T. So if we write that out, we need to find what part of the curve we want. So let me do this instead. We want a 95% confidence interval. So if this is maybe this area is 0.95, remember we need to go from here all the way back. So we need to put in here 0.975, and then the degrees of freedom in this case, if you look at the computer output, you don't see the sample size, but they told us the sample size was 69, so degrees of freedom is 69 minus 2, so 67. When you do that, the critical value is about 2, so if you put that in here and multiply, you're going to end up seeing that the correct answer in this case is going to be letter E. Number 8, a residual plot from the least squares regression line is shown below. Which of the following statements supports the graph? Now, first point of review is to remember that residual stands for actual minus the predicted, so that's a good review. So that's what we're seeing in terms of the actual result minus what the line would predict. So if we take a look at this, which of the following statements supports it? A, the residual plot contains dramatic evidence that the standard deviation of the response about the population regression line increases as the average number of inputs per round increases. Well, first of all, dramatic evidence is a bit extreme to use, so that and alone is going to kick itself out for me. And it talks about the population regression line. It's not about a population, so just knock that out. This is the sample. Part B, the sum of the residuals is not zero. Obviously, there is a major error present. Well, if you compute the residuals for your entire data set and you add them up, they do it comes back to zero, but it doesn't mean there's a major error present. That's how it's computed. It's doing the residuals or the error compared to the average. So when you add them up, the residuals are zero. This doesn't even make sense because there's not a major error. That's just how it works. Letter C. Using the linear regression to predict a player's total winnings from his average number of putts almost always results in error of less than 200,000. So the error, if it's less than 200,000, if we look at it too, 200,000, a lesson would be anything in this range to this range. And those are the ones that have error less than 200,000. Other than that, that's not true. There's a lot of them outside either on the high end or low end, so that's not good. D, for two players, the regression line underpredicts their total winnings by more than 800,000. So underpredicts would say this. If you underpredict it, the prediction is going to be smaller number than the higher, so we're looking at positive values. How many of them are above the 200,000 or 800,000 line? If you look at that, there are two people above it, so this is a correct statement. Letter E, the residual plot reveals a strong positive correlation between the average putts per round. The residual plot doesn't show us the correlation. That's the scatter plot. So in this case, if it said the scatter plot and we saw that, that would be fine. But that's why that one's out too. Number 9, which of the following would provide evidence that a power law model of the form y equals a x to the b, where b is not equal to 0 and b is not equal to 1, describes a relationship between a response variable of y and an explanatory variable of x? What you want to take away from this is a power function. If they tell you you have a power function and you need to linearize it, you guys, all you need to do is you're going to take the log or natural log, it doesn't matter, of x and the log or natural log of y. That's how you handle power functions. Now, what if it's an exponential? If it's an exponential function, what you do to linearize that, you keep x the same and you're going to take the natural log or the log of y. If you remember these two components, you're going to be fine on how to linearize power and exponential functions. So based on this, which scenario answers our question the best? It clearly has to be E. That's how you deal with power functions. I do like the response for B. B is the response for exponential functions. A doesn't make sense because that means you would do nothing. We don't do anything like that for C, and clearly it's not none of the above. So just take away these two features from this slide and you'll be good. Number 10, we record data on the population of a particular country from 1960 to 2010. A scatter plot reveals a clear, curved relationship between population and year. However, a different scatter plot reveals a strong linear relationship between the logarithm of base 10 of the population and the year, this equation here. The least squares regression line for the transform data is here. By the way, notice they transformed the y value using a log, so it was an exponential pattern. That's how you linearize anything in exponential. Based on this equation, the population of the country in the year 2020 should be about what? To do this answer, we are going to use the linearized function. Again, I could tell they thought it was exponential because they took the log of just the y or the response variable. That's how you linearize exponentials. Let's make a prediction. So let's put 2020, which is our input for year, into here. So that'll be the log. And I'm just going to call this the log of y to make it simple for me. Negative 13.5. And then if we put this in, 2020 and simplify. If we simplify the side, again, we're going to have log of y, or population. A number here is going to be 6.7. Remember, for your bases, this is log base 10, so just solve it. We're going to do 10 to this power equals y. So 10 to the 6.7 power equals y. In this case, the population is going to be about 5,000,11872. So the best answer here is going to be letter C. And in terms of the algebra and solving logarithms, this is about as extensive as it's going to have to get for you in terms of solving logs. So do remember how to rewrite a logarithm as an exponent and to get your answer. First free response, number 11. Growth hormones are often used to increase the weight gain of chickens. In an experiment using 15 chickens, 5 different doses of hormones, either 0, 0.2, 0.4, 0.8, and 1.0 milligrams, were injected into chickens. 3 were randomly assigned to each dose, and the subsequent weight gain in ounces was recorded. A researcher plots the data and finds a linear relationship appears to hold. Computer output from the least squares regression analysis for these data is shown below. What is the equation of the least squares regression line for these data, and define any variables you use? Now, instead of just defining the variables on the side, I personally like to put the variables within my equation. So I'm going to notice here that our slope is going to be related to the dose. So in that, our response is the weight gain. So y is the weight gain, so I'm just going to put weight gain. And this is a prediction, so do not forget your hat on that, is equal to the y-intercept, or the constant value, is 4.5459. And the slope is positive, so positive 4.8323. And I'm just going to put in here the dose. If you choose to use x and y, that's fine. If you say this is x and that's y hat, make sure you just define the variables on the side. Part B, interpret each of the following in context. First is the slope. So the best way, I think, to say the slope is to think about it in terms of like rise over run, or, you know, the y over the x. In this case, we know that our explanatory variable, or our input, is the dose, and then the response, or the y, is the gain. So what I like to do is I just come in here and I make my slope look like a fraction so I can see rise over run, and I literally just talk about it in terms of that context. So I'm not going to write this down, but I'm going to say it. I would say for every 1 dose milligram of this, the weight gain is going to increase by 4.8323 ounces. The y-intercept, we do see the y-intercept in here. The y-intercept is just the value, or the constant by itself. In this, basically, I'm just going to say it, is that if there was no dosage given, the weight of the bird would be 4.5459 ounces. Let's define S next. Now, S is actually in the output. It's right here, so let's jot that down first so you have the right value. And I would define that as saying, on average, the least squares regression line's predictions will be off by 3.135 ounces. Standard error of the slope. To find that one, we are talking specifically the slope, which is that dose. So to find the standard error of the slope, keep that straight, is this number right here. So it is this. And let's define that one in context. I would say if repeated many times, on average, the slope of the least squares regression line will be off by 1.016 ounces. R squared, be careful with this one. We will never use this adjusted R squared, by the way, so you can actually cross that off. R squared is right there. So the value for R squared is this. Remember, if you need correlation or R, you can take the square root and determine the direction, plus or minus. Definition of this, what you're going to say is 38.4% of the variation in the weight gain can be accounted for by this least squares regression line. I will tell you all these definitions are incredibly important. I have seen problems in the past where they've asked you to define these as free responses and to recognize them within multiple choices. So please make sure you're comfortable with understanding these. Part C, assume that the conditions for performing inference about the slope of the true regression line are met, so we don't have to check a liner. Do the data provide convincing evidence of a linear relationship between dose and weight gain? carry out a significance test. So they said conditions are met, so we do not have to do the plan, but I do need to do the state, the do, and the conclude. So let's state the hypothesis. So the H sub O for this is that beta is equal to 0. Now the problem says that they believe the hormones will increase the weight gain. So if we increase it, we means we're going to have the slope becoming positive. So I'm going to say H sub A is beta is greater than 0 on this one. And let's use an alpha of 5%. And we would define that it is the slope of the weight gain to the dosage is what the B is for that. The do part's already been done, but let's actually mention that we are going to do the t-test for slope. So it's the t-test for slope. That's going to give us credit. The p-value, if we define that, we can actually go back to the computer output. The p-value for this, you're going to see it's under the word dose, under the p, it's 0.0004. Degrees of freedom, there are 15 chickens, but remember for regression, our degrees of freedom 15 minus 2, so 13. And that would be enough for the do. The conclusion for this one, we're just going to say p is less than alpha, so we have 0.0004 is less than 0.05. Because of that, we can reject H sub O. And we're going to conclude H sub A, and I'm just going to conclude that there is a linear relationship between the dosage and the weight gain of the chickens. Now, part D, they want us to construct and interpret a 95% confidence interval for the slope parameter. Now, because these are within the same problem, I am going to apply that the plan has been done, the conditions have been met. Construct the confidence interval. The thing about this, the state is actually kind of already done for me. So they've stated the problem. The plan has been carried out here and that the conditions are met. The do for this one, if I look at the output, I do not have enough information on the computer output to get to read the confidence interval. I do have to compute it myself. They want a 95% confidence interval, so that's going to be 95% of here. This is a slope test, so remember the confidence interval, if I write it out, is going to be B plus or minus the critical value of the standard error of the slope. To get that critical value, I'm going to do an inverse T of 0.97, and again, we have 13 degrees of freedom on this problem. If we do that, we're going to get a T critical value of being this right here. From the printout, we know that the slope for our B here, for our statistic, is 4.8323, plus or minus the critical value we just computed. And then from, again, the computer output, the standard error of the slope is 1.0164. When you write this out, the confidence interval actually ends up being a 2.63688 to 7.02772. I'm not going to write it down, but the conclusion, I'm going to say it. We are 95% confident that the true population slope of weight to the dosage will be between 2.63 and 7.02 ounces. This last question's a long one, so let's go through it here. 12. Foresters are interested in predicting the amount of usable lumber they can harvest from various tree species. They collect data on the diameter at breast height, which is dBH, in inches, and yield in board feet of a random sample of 20 ponderosa pine trees that have been harvested. Note that a foot board is defined as a piece of lumber 12 inches by 12 inches by 1 inch. Okay. Scatter plot is right here, so we are seeing the data, the breast height of the data, and then the amount of boards that were coming from those various elements that we chose from those trees. Part A. Some computer output and residual plot from a least squares regression line on these data appear below. Explain why a linear model may not be appropriate. So what we're seeing here is the scatter plot. Here's the residual plot, remember, of the errors computer output. Why may it not be appropriate? The scatter plot looks, remember when you see a scatter plot from chapter 2, define your DOFs. So it's a fairly strong positive linear correlation. However, our residual plot does show a curvature, so because of the curve in the residuals, this may not be an appropriate model for this case, which means we should probably try to linearize it. Here now we have the foresters are considering two possible transformations of the original data. First, they're going to try cubing the diameter values or taking the natural log of the yield measurements. So remember, for the regression model, if you look at the scatter plot, our x value or our explanatory is the dBH. The y or our response is the board feet or the lumber that they get from it. So if that helps you kind of keep it straight. So they either want to come in here and take the natural log, what they're saying in part 2 of the y value, or they're going to transform the cubing the diameter values. So if we take a look at this, option 1, they've already done it for us. They came on in and they cubed these values, and they got this equation. Option 2, they took the natural log of the yield, which is the y. So from here, use both models to predict the amount of usable lumber for 30 inches. Basically what we need to do is write the equation and make a prediction. So from here, you can also see what they did is the dBH was cubed in that case. So I can write the equation. What this would be is the yield, or the board feet, by the way. The yield hat is going to be equal to the 2.078, and it's plus 0.004. I'm just going to put a 3, and this is going to be of the inches, in this case of what they're using, cubed. Now I'm going to compare it to this other model. And on this one here, let's make a little bit of room. The second equation is going to be the natural log of the yield height is what they're doing. Hat is equal to 1.2319, and this is going to be plus 0.1134 of our inches. By the way, keep in mind for the second one, this is an exponential assumption in that they're just taking the log or natural log of the response variable. Make a prediction for both. We can easily do that. Let's just put 30 in. If we put 30 here into the inches, and if you simplify that, I'm going to tell you on this one what you're going to end up getting is 117.07. On here, if we put 30 in for the inches and simplify, we'll get it down to the natural log, and I'm just going to call it of y. That is going to be equal to, my value here is going to be 4.6339. Now to rewrite that one, natural log is just log base e, so it's going to be e to this power equals y. So I can write it as y equals e to the 4.6339 power, and that would give me about 1.2915. So those are our corresponding predictions using each of those two models. Part C, which of the predictions in Part B seems more reliable? Give appropriate evidence to support it. Well, basically, we do have the residual plots for both of the models. This is the one where they cubed. This is the one where they took the natural log. And again, just knowing that they're lined up here is how you know that. The pattern in this first one doesn't look too bad. It's scattered. There's kind of some equal distance. This first one does have or the second one here does have a U shape, which I don't like. So based on that, I would recommend, in this one, we do not like the second model, which would be taking the natural log of the yield. The one that would be more preferable is the first one of cubing. So based on that, for the prediction, the better prediction on here is going to be getting the 117.07 because the residual plot shows no pattern and there's random spread around it.